Okay, I wanted to start discussing section 3.3 and 3.4 of the book. So, the way I'm going to do it, I'm going to start talking about linear motion. Okay, so there's two specific types of motion I want to analyze first, which is simple sort of linear motion and uniform circular motion. Okay, so let's go ahead and look at that. Okay, let's look at linear motion first. T is always going to represent time throughout. So we imagine some particle moving in the plane or in space, okay, through time. Okay, so this is going to be very physical. And we think about a path being traced out by that particle over time. Okay, and then we talk about various derivatives and things like that associated with that curve. Okay, so imagine a particle moving through space in time. The position vector of that particle I'll call r bar of t because it depends upon t. Since this is linear motion, I'm going to have a fairly simple equation governing the actual path of the particle here. X naught, y naught, z naught, you can see that's a vector there. That's going to be the position vector from some starting point, okay, from some starting point here. And I also have here plus f of t, t naught hat. T naught hat here, this is going to be a particular direction vector. You can see with the hat on it in my notation, as often done in physics. That means you're dealing with what, a unit vector or direction vector. And f of t here, this is just a scalar multiple of that. Okay, so you can see what we're doing is starting at a particular point, and then we're moving off in a certain direction, okay, a certain fixed direction. Okay, that direction again is t naught hat. The reason I'm using a t, by the way, is because t stands for tangent vector. Okay, this is linear motion. It's definitely tangent to the direction of motion, right? Okay, all right. But this is going to be a function of time f of t here. Now, what I call v bar of t is velocity, okay? So this is going to be the velocity of the moving particle as a function of time. That's going to be a vector, right? We don't want to mix this idea up with speed. We'll talk about speed here in a minute. But v of t, the velocity then, is the derivative of the position vector with respect to time. So I wrote that here, r prime of t. Now, if I differentiate this constant vector, I just get 0, so I'm ignoring that. This is fixed. This is supposed to be constant, so that's t naught. That stays, so all I'm really doing when I differentiate here is differentiate the scalar multiple on t naught, right? So I've got f prime of t times t naught here, okay? Now, we're going to make this assumption. Okay, it may not be true in many cases, but we're going to make this assumption that f prime of t is always going to be greater than or equal to 0, okay, in other words, for all time t. So that means it's not going to backtrack along that line, okay? So it's going to keep, it may stop, but it's going to keep, it's never going to backtrack along that line, okay, the particle that is in motion. Now let's go ahead and talk about arc length here. This is completely consistent with what you're reading and what you saw in Calculus 2 here. But let's talk about this. What is arc length? Okay, arc length S, it's not a 5, that's an S. S is a function of t, okay? So what we imagine, we're starting from that fixed point and we're moving in that particular direction. We're talking about what arc length along that curve. By the way, when we say curve, that would include a straight line, even though there's no curve to it, right? Okay. There's different ways of defining this, but this is, like I said, is totally consistent with Calc 2. Okay, here's our way of doing it. From whatever our initial time is to our particular time t, okay, we're going to integrate the following here. The magnitude of the velocity, okay, over time. By the way, I had t's there and then scratched them out because I'm really using u here as a dummy variable and a variable of integration, and I'm integrating from the original time, which may be 0, it may not be, up to whatever time t is. So you see in this expression here, the upper limit of integration is the actual variable here defining this function s of t. Okay, u here is just an integration variable. Okay, all right. Now you remember v is also what? The magnitude, or I should say r prime. Okay, again, substituted u in there, and I've got magnitude around that. Okay, now let's see. If I take the magnitude of r prime, that would just be the magnitude of this vector, right? Okay, but the magnitude of t hat is 1, so I'm really just looking at the absolute value of f prime of u. And I stated up here that I'm assuming that f prime always has non-negative values here. So this would actually be my final expression for arc length, okay? It would just be the integral from t naught to t, f prime of u du. Now the reason I'm doing this, let's see if this makes sense to you here, is let's reverse this for a second. Speed, what is speed? Speed, you all know, is a scalar, right? It's actually the magnitude of the velocity, but you could, so that's what I have written here. But it also means this. It's the rate of change of arc length with respect to time. Now this isn't just for linear motion, this is a completely general here. Okay, so what I've got up here is general. This second line here, this is specific to our situation there. But does that make sense? Speed is actually how quickly you're eating up distance with respect to time. Remember, s is distance along the curve from some fixed point. That's what we're calling arc length. But anyways, that's the magnitude of the velocity then, according to this up here, which is actually ends up being f prime. Okay, so the speed turns out to be f prime. Again, don't forget we're assuming that's greater than or equal to 0 in this case. How about acceleration? How is acceleration defined? Acceleration is defined to always be what? The instantaneous rate of change of velocity with respect to time. Now again, this is calculus 3, so we're using vectors here. Okay, so you can see a bar of t equals v bar prime of t. So that would be what? Wait, v bar is actually r prime, so this is going to be what? R double prime of t. Okay, and if you actually look what this is, if I differentiate this, I would get what? F double prime of t, t naught. Okay, by the way, I'm not making any statements about this. This might be positive, negative, or whatever, right? Something could be accelerating or decelerating along that line. Okay, now if we come up here, another way of saying that is, do you see the second derivative of arc length with respect to time would give us the f double prime. So right here, in place of that, I'm going to put f double prime, or in place of f double prime, I'm going to put the second derivative of arc length with respect to time. So we could write acceleration this way in the case of what? Linear motion, that it's the second derivative of arc length with respect to time times t naught. Okay? This component of t, I'm going to sometimes call linear acceleration or tangential acceleration. We'll see in a greater context why I call it that, okay? Because this is going to reappear again in general motion. Okay, so I either call that linear acceleration or tangential acceleration. Often I just call it tangential acceleration here. Now that's a scalar. You see, I'm referring to that fellow right there. All right, I'm calling it acceleration, but it's really what? A scalar, right? So we have to remember which things are vectors and which things are actually scalars. Okay, let's talk about another form of fundamental motion here. This is going to be uniform circular motion. Now, the way I'm setting it up, you could change the situation if you wanted to. It's not going to make any ultimate difference with the formulas I want. But I'm going to assume that the motion here is in the xy plane. Again, t is time. That's little omega, that's not w. Just in case when I'm reading it I say w. It's actually supposed to be little omega, right? That's angular speed. Do you know that? In physics, little omega is often used as angular speed. In this situation, we'll see uniform circular motion. This is going to be constant. I'll say, okay, so I could write omega naught here, but I'm just going to leave it as omega here so I don't have to write so much here. Okay, now I'm just going to assume that I've got a particle or something moving uniformly, in other words, with a constant angular speed centered at the origin in the xy plane. Now the radius of motion here is going to be cap r, so that's the radius of the circle. Now I'm assuming that's a positive number. I'm going to be making that assumption also. Okay. Also up here I'm going to do the following. I'm going to assume that omega, little omega here, is also positive. Okay. So we can see here if it's moving in the positive direction, we're moving counterclockwise. Okay. Okay, it doesn't absolutely have to hold here, but that just makes things easiest for this situation. Now, let's talk about position vectors of points on that circle. Would be what? It'd be r cosine, go back to trigonometry, r cosine theta, r sine theta, right? Now that r is a capital R. That's a distance from the origin about which it's circling here. And our theta here, right, that's the angle measured with respect to what? The positive x-axis. Our theta here, I'm going to only reference verbally, that's actually what? Omega t. Okay? So that means when time is 0 here, that means that it's actually starting at the positive x-axis. Okay? So we'll assume that this holds here. Okay? All right. Now let's start taking derivatives and stuff. Okay, let's start talking about velocity. To get the velocity, what do? I differentiate position, right, with respect to time. So if I differentiate this expression, this vector, with respect to time, you can see from the chain rule that little omega is going to pop out of the formula here. And I'm going to also take the r out. So I've got out front r omega. When I differentiate cosine and sine, I get what? Negative sine omega t, comma, cosine omega t. And that's going to be the velocity. Okay? By the way, now if you look at this expression here and go back and look at a picture, I claim the velocity up here is actually tangent to the circle. Okay? Okay, it's actually tangent to the circle here. So that this vector v is actually orthogonal to the position vector there. Now I don't know how long it is. That would depend on on omega here, which we don't know anything about in general. Okay, except that it's positive here. Can you go ahead and prove here that this is actually tangent here, so that these two are orthogonal? And no less, can you prove that it would actually be taking the direction of this vector and rotating at a positive pi over 2 radians? Okay, so I claim I have the direction here correct also. So it's going to be pointing up there towards the northwest in my picture. Okay, can you prove that? Okay, it's easy. Take the dot product of these two and you'll see that it's 0. Also add pi over 2 to each of these on the inside and you'll see that you actually get this unit vector here. Okay, take out that cap r though. Anyway, let's go ahead and do this. Let's talk about speed now. What was speed? Speed is the magnitude of the velocity. So let's take the magnitude of this fellow. You can see this is a unit vector right here, so that when we take the magnitude of this, all we're getting is the scalar r omega, because both r and omega are positive here. Okay, there I've stated it explicitly. Okay, so the speed is r times omega. You can see that that's a constant r also, right? Because cap r is fixed and little omega is also a fixed constant, okay? So it's moving at a constant speed, okay? So uniform circular motion, we said originally we were talking about fixed angular speed, but that also corresponds to what? A fixed actual speed along the curve, okay? Now that we've got that down, let's go ahead and, for my notation, let me throw this in here. Do you see I've got v of t? Now this can be a dangerous notation unless you're careful here. V of t is actually what? The magnitude of v bar of t. Notice how I just got rid of the bar? Okay. Now you can do that, but this is kind of dangerous for when students do this because they're often dropping bars anyway. Okay. But v of t is going to represent speed if there's no bar on top. And that's r omega anyway. Okay, let's go on. Let's go to acceleration here, the acceleration vector. So I'm going to do what? I'm going to differentiate r prime of t. I'm going to be differentiating the velocity. So I get r double prime of t. And so I'm going to differentiate this guy one more time. And you can see I'm going to get another factor of omega. And the easiest thing to do is also factor out a negative sign here. So you would get cosine omega t sine omega t. And then you've got actually, you notice this. This is actually, if I put that r back in there in the original, I've got negative omega squared r of t. That's the original position. So that you see the acceleration in a situation like this, uniform circular motion, you've got an acceleration which is pointed in the opposite direction to what? The actual position vector. Now it's a scalar multiple here. You've got omega squared, which is positive. But notice that minus sign on the front. So that means the acceleration is pointing what? Inward. Okay, the acceleration is pointing inward like that. I hope you see that little arrow in there. I'm imagining attaching it right here. So you've got like a little vector. Here's our acceleration vector with the initial point at the particle at any particular point in time there. Okay, it's pointing inwards. By the way, so we write this, A equals A of t, right? That's r double prime. And I'm going to rewrite this slightly. Now I've called that r prime of t the direction vector for the original, right? So that's pointing outwards. Okay. Just do a little math here for a second. I factored out an r from r bar to get r prime, because the magnitude of r bar is r. Okay, so you can imagine an r squared here. But I've got r omega squared on top, so those would cancel here. Well, what's r omega? R omega is actually what? Speed, right? Okay, notice that I've got v here then with no bar in it. That means speed. And I've got negative v squared over r times what? The original direction vector that was pointing outwards from the origin. But that's a unit vector. Notice the hat on there. Okay, because I want to look at the scalar here. Okay, now that's pointing inwards though because of the minus sign. Okay, let's look at the magnitude of the acceleration. That's going to be a constant also. It's going to be what? The speed squared divided by the radius r. Speed squared divided by r. Do you remember something called centripetal force? What is force? Magnitude times acceleration, right? Now I'm going to write it as a vector. Okay. Do you remember this? Okay, I could multiply that by m, and I've got that direction vector. It's pointing on the inside. Its magnitude would be what? mv squared over r. Do you remember that's the magnitude of centripetal acceleration? Okay, mv squared over r. All right, well, this shows you why that's holding here. Okay, one last thing I want to discuss here. This is not motion as such, but I just want to talk about arc length as a parameter in preparation for some of the stuff we're going to be doing next here. In physics, we often use time as a parameter. Again, a particle moving through space or the plane even in time. Another great parameter that's very geometrical is arc length. Okay, so here's the idea. I have some sort of this is supposed to be smooth here, but it looks a little choppy. But let's just assume it's smooth, okay? I've got a smooth curve that you could imagine being swept out by a particle, but instead of using time as my parameter, I'm going to say I have a starting point here, okay, where s is 0. Remember, s is reserved for arc length. And then what? I can imagine every point on the curve being associated with what? A particular value of s, right? That would be the distance along the curve you would have to travel to go from the initial point to the final point here that I've x'd here. And that's a value of s. Now, if you're going in circles like this, you can have multiple values of s actually corresponding to the same point. Okay? But that's okay. That's not going to bother us here. One of the things we are going to do here, though, is assume that S increases with increasing time in my calculations below. Okay, so whatever I call S, okay, will be moving in a particular direction along the curve in time, and S will also be increasing along that curve. Okay, so we're going to assume that the speed is never, it's always positive, it's never even a zero here, okay, in my calculations here. The stuff I do below here would still be true, but they're more complicated arguments here. This will give you the basic idea here. Now, position vector, okay, that's a position vector of points on the curve, okay, so that's R bar. I'm going to imagine those parameterized by what? Those points are parameterized by arc length instead, right? How far down the line, down the curve do I go to reach a particular point, right? Okay, R of S. Now, let's go ahead and talk about taking derivatives and taking magnitudes here. Suppose I differentiated this thing, well, really this thing, with respect to S, not with respect to time, but with respect to S here, okay? All right, and then I'm interested in its magnitude here. I'm going to show you something here. That's the magnitude of R prime of S, and I claim that's going to be 1 for all S. In other words, dr over ds is always going to be what? A unit vector, I claim. That's always going to be a unit vector. All right? And we're going to see why that is, and we'll get an idea geometrically why it is. Okay, let's go ahead and think of it the old way here. Dr over ds, okay, just consider that for a second. That's dr over dt times dt over ds by the chain rule. Okay, that's dr over dt divided by ds over dt. And you can see here that this is going to be what? Wait, that's going to be velocity, and this is going to be what? Speed, or the magnitude of the velocity. So I've written those here, although I didn't write v here. But you can see that this vector divided by its own magnitude is going to give what? A unit vector, right? It's going to be a unit vector, and I call that t hat, and I happen to have that parameterized with respect to s, right? So that's t hat. What does the hat mean? The hat means it's a unit vector, right? What does t stand for, the cap t? Tangent. This is going to be a tangent vector here. Okay? I hope that makes sense. Let's talk about another way to give you the idea here. Suppose I have my parameterized curve. Here's the initial point at what I'm calling O. Okay? And then we're moving along that curve with increasing values of s. Okay? All right. So let's say I'm at some particular value of s, I'm at point P, and some larger value of s, in this case geometrically it looks like I'm at some point Q on that curve. So here I'm at R of s, here I'm at R of s plus delta s, some change in s here. Okay, delta s would represent what? The distance along the curve traveling from P to Q. Okay, let's consider looking at this expression, okay? R of s plus delta s minus r over s divided by delta s, okay? You can look at this. This would be what? This would be the position vector, the difference in these position vectors. So that would be the vector from what? P to Q right there. That's what this thing represents right there. That's that vector I've tried to go in there. From P to Q. Can you see that little arrow on there? Okay, and then I'm taking that vector and I'm dividing it by what? The actual value of delta s. Okay, all right, because we're interested in taking the limit of this as delta s goes to 0, because that's my expression right up here, right? That's my definition of derivative. Okay, I would take the limit as delta s approaches 0 here. Okay, anyway, let's go ahead and do this. Now I'm going to rewrite this slightly. In place of delta s, I'm going to put in the actual magnitude of the vector from P to Q. Okay, so I replace that here, here, and here, so these two would cancel out, right? And these two expressions would still be equal. Okay, now clearly, hang on a minute, this is a unit vector, right? This is just what? The vector PQ divided by the magnitude of the vector from P to Q. So this is always a unit vector here. Okay, that's a unit vector all the time. This is not a unit vector, but we're going to see something that happens here. This is actually what? The distance PQ divided by delta S, you can see that PQ is actually always going to be a little bit shorter than delta S unless you're moving along a line. Nevertheless, the idea is if we take the limits as delta S approaches 0, this is going to end up being what? 1 also. Okay? That's going to end up in the limit being 1. Does that make sense? Do you guys see as delta S approaches 0, the ratio between the length of PQ and the actual arc length, on a smooth curve at least, will actually go to 1 here in the limit. So this is approximately 1, and it actually goes to 1 in the limit. So that's what I have here. So this actually means that in the limit, as delta S approaches 0, R prime of S is T hat of S. In other words, it is indeed a unit vector. Okay? All right. So that's the